Welcome to the Hedgineer Podcast, hosted by Michael Watson.
Hey everyone, and welcome back to the Hedgineer Podcast. I'm your host, Michael Watson, where we talk about technology, data, and AI within the asset management and hedge fund industry. Today we have another special guest, and it's thematically building on last week's episode with Rusty Conover, where we talked about a really powerful embedded database focused on columnar storage called DuckDB. And this week, we're bringing on Prashanth Rao, AI engineer at Kuzu, which is a parallel concept where it's an embedded database focused on graph databases. And us at Hedgineer have been using it pretty prolifically over the last couple months to construct our own knowledge graphs and have been pretty blown away both by the portability that you get from the embedded database model, the performance of Cypher queries on top of the Kuzu protocol, and use cases within AI workflows to build out knowledge graphs, interact with agents, and reached out to Prashanth, seen him back and forth on LinkedIn a couple times over the years. I've been following Kuzu since the launch out of Waterloo, and I'm excited to have you on the episode, Prashanth. Welcome.
Hey, Michael, thanks a lot. And it's great to be on the show. And first of all, thank you very much for using Kuzu and talking about it.
Yeah, definitely. So I would love for you in your words to give a quick introduction on Kuzu, what it is, and how it differs a little bit from historical graph databases like Neo4j, but also give a quick intro of what is a graph database and what are the best use cases.
Absolutely. So Kuzu, as you mentioned, it's an embedded graph database, but it's built for query speed and scalability right from the ground up. So the way Kuzu achieves what it does is it fundamentally changes the design principles that people may be used to from other graph database systems, which are mostly client-server based. But Kuzu, just like DuckDB, is an embedded database, which means it runs in process. And this means that it's basically optimized for handling complex join-heavy analytical style queries. By join-heavy, we mean queries that have multi-hop paths. And these are traditionally very, very expensive queries, even in graph databases, because as you can imagine, as your data grows larger and larger, you have a combinatorial explosion and you have nodes that branch out into other nodes, and recursively traversing these paths and collecting the results and aggregating on them can get really expensive. So Kuzu's design basically focuses on getting the maximum performance out of those kinds of queries, while also making it highly usable by providing a similar query interface like people are used to from other systems like Neo4j, by providing the Cypher query language. So we can go into certain details that you want to dig into deeper, and yeah, we can go from there.
Yeah, definitely. I mean, one of the things that I was initially surprised on when I first started using Kuzu is the almost static typing of the DDL. Like you explicitly call out your tables or your nodes and your edges with explicit fields or attributes on both of these. When I came from a Neo4j or anything that's more like I just generally bucket into a NoSQL database, they tend to be unstructured, that you define whatever your keys, your values, your hierarchies are, however you want. But then with with Kuzu, you guys make the opinionated approach of saying that we want to predefine the structure. And I'm curious why that is.
That's a very good question. So the fundamental reason for having a strictly typed system in Kuzu is just like DuckDB, Kuzu is actually also a columnar database. What this means is the underlying node representation in Kuzu is essentially a table. Just like you have a table in a relational database like DuckDB, you also have the concept of a node table in Kuzu. And a node table has columns. The first column in the node table is a primary key column, which is used for identifying unique nodes. And also the remaining columns represent the properties. Now, the advantage of having this structure is, first of all, by having a columnar structure, you can efficiently process batches of records at once rather than one record at a time. And then, of course, now with the columnar structure, you essentially have this idea of type safety or strict typing, just like you have in relational systems. So to gain the benefits of this typical columnar analytical processing that you have in other systems, Kuzu inherits those principles and brings them over into the graph database space, which is actually a fundamental difference from other systems out there, because most, as you mentioned, most graph database systems are kind of like NoSQL, where you don't have the concept of strict types. Now, the main benefit of this, as you can imagine, is you have massive performance gains, because based on having this columnar structure and knowing the types beforehand, you can actually make a lot of assumptions about the types that are existing in every column. And that allows you to apply a lot of customizations and optimizations, including things like compression techniques that are very common in other OLAP systems. So Kuzu brings like a blend of the benefits of relational, columnar, analytical sort of query processing, but leverages the power of the data models that are common in graph databases, like the property graph data model. So it's actually a very unique blend of property graphs with structured types.
And it's, for us, it's been pretty refreshing because you made the design decisions that it seemed like we're almost for optimizations of query time performance by having it be predefined, helps it be compiled, it helps with the columnar sort of structure, but it also forces the designer to be thoughtful on the relationships ahead of time and then rely on the DDL to be able to ensure that, like, we're going to adhere to this schema until you make a conscious decision to change it. And although it does put more upfront planning on the designer of the graph, it actually allows for more thoughtful workflow once you start making it more agentic in terms of having an AI potentially determine the values of the attributes on an edge, or defining the edge itself, identifying that two entities are actually related to each other, that it can leverage that predetermined strict schema that a user or a human can define, but then allow it to be a little bit more free in terms of instantiating those edges or instantiating those nodes. And I'm curious on how you've started to see a increased adoption in graphs in general because of AI and agentic workflows that is causing a resurgence almost in thought and the zeitgeist around graph databases and knowledge graphs in general.
That's very interesting. So
how has that affected adoption of Kuzu? Like, I don't think Kuzu was built with AI in mind, yet it seems to be something that is now tightly coupled with this agentic revolution that's happening that probably wasn't on your plans when you started the project, but it is getting a ton of acceleration because of it.
Yeah, fascinating. So Kuzu actually came out of University of Waterloo as a research project many years ago. So you're right that it predates LLMs by quite a fair amount. And when Kuzu was designed, I think it was mainly because of the benefits of what these modern columnar systems do, analytical systems from other paradigms are brought into the world of graphs. Now, those are designed for traditional graph workloads where you have these expensive recursive queries that you traditionally write with a lot of joins. But what we've noticed actually in the last 2 or 3 years, as you pointed out, is ever since the advent of the GPT models and the transformers and all the other LLMs that have come about in the last couple of years, there's been a resurgence in interest in how people think about graphs and how they relate with the LLMs that we have today. And the main reason I think this is happening is, if you think about what a graph really is, it's essentially a way of imposing structure. And the structure in a graph is very, very specific. You have the concept of nodes, you have the concept of edges. These represent concepts in the real world. And now you map this onto the existing data that we have out there that LLMs process, right? We have unstructured data like images or text. We have all sorts of various forms of data. And LLMs are really good at interpreting parts of this data. Now, the challenge comes in when you're building things like RAG, where some of the data is unstructured, but when you chunk those up, you don't necessarily model those relationships or connected information in that data explicitly. Where a graph really comes in is you can actually capture the structure in that data that was otherwise unstructured. And LLMs are actually really good at the upstream and the downstream stage of this. In the upstream side of things, there is a structured output extraction, which is transforming the unstructured data into a structure that represents a graph. So during graph construction, this is a very powerful concept. But then downstream, the LLMs can also help you where you have a graph and now you're trying to query it, but the user may not necessarily know Cypher or the query language that the graph uses. So now the LLM can be that natural language interface that the user needs, but translate the natural language down to the query layer, in this case, Cypher, and then retrieve the information and send that back to a downstream agent or any other application. So this is, I think, why there's so much interest in graphs after LLMs have taken off, because although graphs have been around for a long time, they've been used for a lot of other specialized use cases like recommendation systems and expensive analytical systems. Now, currently, they are kind of at the blending zone between where people are building AI applications and then they're bringing in all the traditional data processing techniques from the world of graphs.
Totally. And I think it's interesting how you identified that it's both beneficial in the graph construction, but also in the graph traversal and query side. I think that graphs, in my experience, have just been hard to A, maintain, and then B, to access. And on the maintenance side, if your graph is not your primary storage mechanism, which a lot of graphs, they're not primary storage in the sense that if you have a bunch of likes or you have like relationships or you have products, your primary store of those concepts is not in the graph itself. It is actually in maybe your ERP system, or it's maybe in a relational system that captures all these transactions, and then it gets translated to the graph to be able to do this more complex relationship mapping across multiple nodes via various different pathways. But keeping that graph up to date can become challenging as you want to capture more and more information about it. Like maybe you want somebody's bio or around a customer, and then you want where they worked, and then where they went to high school, and now information about that high school, and who was their teacher, and what was the subject that they taught, and what books were in it, and then what are the actual authors of those books. Like as you go down this weird rabbit hole, all of that information may be relevant for use case. I'm sure there's very few use cases that went to that rabbit hole that I just went down, but keeping that knowledge graph up to date on whatever domain or enterprise that you're working in has been a tremendous effort, requires a lot of human curation. And up until now, very few organizations have that type of resources in order to do that level of curation, and have punted on trying to create a graph that could represent those relationships because it's so resource intensive. And at least in our experience, actually, like once you have a predefined set of attributes and nodes and relationships with some examples in chain of thought, you can then use language models to go and start constructing that graph based off of the data that you do have without having to add a significant other layer of human curation or a lot of new systems or processes or servers to figure all that out. Like language models are pretty good at like the construction side, but then on the flip side of that, they're also very good at constructing text based off of very well-defined inputs and outputs. And that text in this case is a Cypher query. And so it's also like most people don't know SQL, or most people know a little bit of SQL, but then saying, oh, I'm going to throw Cypher at you. And you look at these arrows and they're going left and right with brackets and parentheses. I will admit, once you actually read Cypher, it's very human readable. But the first experience is a little bit of a, oh my God, what is this language? Is this like some weird Perl regular expression that I have? I'm having trauma just thinking about that from the first time I worked with Perl regular expressions. And so you get that barrier of entry into Cypher as a whole. But then it is somewhat complex. But language models are excellent at that, of traversing that question, be able to understand the DDL of the graph, and then constructing the Cypher query for you, which then unlocks this downside use case of being able to interact with a graph and having a language model do the graph traversal via understanding Cypher. And combining those two together suddenly make this barrier of entry on the creation side and the barrier of entry for having engineers or technologists that can actually access the graph. Both of those go a lot closer to zero than they were just 3 years ago. And then there's obviously the use cases of how you can actually use that graph. And that's where I'd be a little bit curious from your perspective. I mean, we have a lot within ours of asset managers, hedge funds, of how we create a knowledge graph that bridges front, middle, back office. And front, we can go really deep on the research side. Back office, we could go really deep into internal processes, systems. But there's a whole other world outside of the one that I live in asset management in the hedge fund space. I'm curious what you're seeing where within the graph ecosystem, where you're seeing the most amount of adoption and use cases for graphs and knowledge bases.
Yeah. So those are very fair observations to begin with. The part that you mentioned where graph is not the primary store of data is a very common one. So I worked in a number of industries before I joined Kuzu. I worked in banking industry. I worked in healthcare, in the chemical industry. So there's been so many different use cases I've worked on where you're right that graphs are a part of the whole stack, but there's always a primary store, typically some sort of relational system, or even things like MongoDB, like a NoSQL store, where a lot of the original data is stored, but then we transform those into graphs. So that being said, graphs are such a generalizable data structure and such a widely used sort of model for different applications that they apply to pretty much every industry. And in my time using these different systems, I worked with different query languages, different data models, and of course, a lot of time spent with graphs after joining Kuzu. I'm seeing a lot of, there's a bifurcation between the people who use graphs with the AI ecosystem or LLMs and the people who use graphs the traditional way, which is interfacing with structured stores like a relational system. And again, going back to what a graph really is, it's essentially nodes connected to other nodes via relationships. And if you think about what a SQL table is or relational table is, you have columns and you have potential foreign key relationships between these columns, which essentially represent edges. So you may have multiple tables in a relational system and you have edges between them formed from the different columns that are common between them. So that's essentially a different way of modeling your data. You essentially had the data in a relational store, you're transforming that into a graph. So Kuzu very easily fits into that ecosystem where you can actually plug into a relational store. Kuzu provides extensions where you can actually directly, for example, connect to a Postgres table, read or scan from it, and then bring that data into a graph. That's one way of thinking about things. The other way of thinking about things is exactly what you said, where you don't have the data structured upfront and you want to use an LLM to actually transform that into the structure. And you bring those into a JSON-like representation or some kind of structured representation, and now you can ingest that into a Kuzu graph. So the design of Kuzu actually makes this very feasible for a lot of organizations. And the main reason for this is when you have an embedded database, it's essentially running in process. This fundamentally reverses you could say the direction of data flow that people may be used to, where in a traditional client-server system, your primary store is sitting somewhere remotely, let's say on a server in Postgres or somewhere else. And now you want to bring that data into another server-based database. So you have this whole ETL job where you have to move data between these systems. And ETL, as you know, as you mentioned, can get quite burdensome when you have a team that has to maintain it and you have people who need to know the languages and all of that. Now, that being said, Kuzu still does use ETL, but the way you do the ETL is quite different in the sense that because it's embedded, you just point it to the source. It's running as a process, essentially a file on disk in your machine. So you very easily move the data into the graph. Now, there are ways you can use Kuzu fully operating on disk, which is the default mode, but you can also operate Kuzu in memory. So now this opens a whole new layer above this where you could run an ephemeral workload. You don't necessarily need to persist the graph. You could literally just read from whatever source you have, potentially point it to an LLM, extract something on the fly, validate the data using Pydantic. There's so many ways you could think about gathering the data upstream, running an in-memory graph database. Depending on the size of your instance, you could actually scale this up to millions of nodes, depending on how much memory you have. But the point is that when you run it this way, it's basically an interoperable query engine, right? You can basically move the database to where your data sits. It's not really operating as a classical database in that sense. It's just a query engine running on top of your data. So there's so many different ways we've seen people using graphs. I think that's unlocked by this architectural decision of Kuzu of running in process, while also unlocking the flexibility of the property graph data model and the Cypher query language and so on. So all the use cases that people run in traditional graph databases via Cypher are easy to do in Kuzu, but you gain that added benefits of flexibility of data movement and all these other things I mentioned.
It's kind of funny. We had a client where we demoed everything that we're doing with AI and knowledge graphs. And they asked me, so this sounds great. I love what I'm seeing, but a knowledge graph, how do I actually sell the CEO, the CIO of a fund, and like why I actually need a knowledge graph, and help me do that more effectively? And one of the things that I was walking them through, I started explaining, is like the knowledge graph is not the thing. The knowledge graph is the thing that can get you the thing, but within that thing that is the knowledge graph, it represents the single best source of truth for how your enterprise is connected together from the upstream systems that you're dependent on. And in our world, that's things like Geneva for your shadow nav, or HedgeServe for your fund admin, Bloomberg for market data, Refinitiv for maybe another source, your Wall Street office data maybe for some bank loan information, and your research data that's all running within Snowflake. The processes that sit on top of that for your fundamental teams and how they're building out their models, maybe tied to Delupa or a Visible Alpha, how they then compare that to consensus and identify deviations between what your internal research team thinks about and the market, how you then ingest information from Axioma or Wolf from a risk perspective, and then construct a portfolio with your risk team on top of that research to be able to hedge out your factor exposure and then turn that into a actual portfolio by entering that into your EMS system like Castle that then produces all these trades intraday that flows through to your back office and a set of trade files that then your reconciliations and operations team has to then confirm or settle into your shadow nav system, and then also gets to your fund admin. You then have to deal with cash and how that interacts with your treasury team and your broker files for expenses. How all of that then flows into your portfolios, end of day positions, and you produce and strike a NAV. You have an investor base that is also asking various questions and wants to know what their fee structure has looked like. You have prospective investors that want to know what would their theoretical fee structure look like. You then have to get all of that information at the end of the year and be able to identify what your compensation structure looks like based off of what analyst performance was. And it's not always black and white based off of how you have different sleeves of the portfolio, and have that feed back into a portfolio construction process that can learn over time. And so all of these different pieces of running a modern asset manager or hedge fund are very disparate. They are silos of information, and they are operational workflows that are not understood by any one person, let alone somebody that can go and actually query the data that is being used to drive those decisions or tell you where in some code base that was maybe developed 5, 10, 15, 20, 30 years ago is existing and how it's being run to orchestrate this whole thing. But the whole thing is being orchestrated. It's happening. The organization is not falling apart, but your ability to understand those interdependencies across that entire machine is decentralized across dozens, sometimes hundreds of different people, where none of them actually understand what the entire machine is doing. And the people that are senior leaders are honestly just trying to keep the thing from falling off the rails, but nobody has control. Nobody has a single source of information or knowledge about the enterprise and how all of that fits together. That is the knowledge graph. That is the representation of the flow of information and the decisions being made throughout the enterprise in a single system that can define what the different entities are as nodes and their relationships are as edges, far better than any other database or data lake effort or technology initiative that have been put in place thus far that have likely always failed at one point or another to capture this. Like, the knowledge graph is an attempt to actually do that systematically. And when I had said earlier in the episode or at another point in time that the knowledge graph before AI was so labor intensive on both the construction side as well as at the query side that it was never worth the actual cost of implementing. But now we're living at a time where we have access to very cheap intelligence that you can scale out to make these don't build the entire knowledge graph for me, but just determine what is the actual trade fee that we're getting from this one broker file for an end of day report. Another job's telling me how much we actually have in cash on swap within this swap facility. Another report or another agent is just telling me what is the relationship between this issuer and entity? What is the QSIP on this specific report? These micro decisions. In isolation, it's not that complicated. At the whole, yes, but that's what we're for. That's why you have experts and human beings that have done this before that use AI to leverage their strengths and their skill sets. And the knowledge graph comes in because it's the best tool in order to capture all of that information. And so what is the knowledge graph? The knowledge graph is the single best expert that you've ever had within your organization to understand what the hell is going on, that if any other person in that organization gets run over by a bus tomorrow, you have that knowledge graph for somebody else to come in, ask, hey, I'm new at the job. I'm the new CTO in town. What's going on? It's codified in a system that's up to date. But AI is not just helpful on the construction. It's suddenly incredibly powerful on the read side, that it can traverse that graph, tell you when you have a report that's going to a CEO that says, hey, this is our NAV. This is how much we have collected within fees, both for incentive as well as performance, as well as these are the fees that we're sending out in terms of technology budget, broker fees, individual fees for interest. How are those numbers being used in this NAV calculation? Well, let's go to the upstream reports, vendors, and systems that can not only tell you this is the truth of data, but traverse the entire source of information throughout the graph. And right now you need teams of people in order to answer that. And you hope, put your finger in the air that it's right. This is a system that is incredibly powerful for both reads and for writes. And then you put on AI on top of that in order to expose that graph through an MCP server, through Anthropic desktop, through ChatGPT, and you're off to the races. And it's just getting better and better and more powerful every week. And it's something that's completely transforming our company at Hedgineer, because this is what we build day in and day out. It's allowing us to scale collecting that information within the enterprise. And it's just changing the way that I think information flows through asset management across the entire industry.
I just have one thing to add to this, if that's okay.
Yeah, sure. Come on in.
Yes. Yeah. So basically, my observation, I worked in multiple organizations before this, and I've seen projects where you attempt to build one large graph from all these different sources fall apart because, as you said, there's too many moving pieces, and not all organizations provide the data at the right time in the right format when needed. So where I'm seeing this today is, thanks to the power of agents, we can actually interface multiple smaller systems together in a very powerful way. And DSPy makes this a lot easier. That's just one of the ways people are doing it. But under the hood, you could have many small graphs rather than one large graph. And this many small graph concept is essentially you build incrementally in subsets of your organization, where you obtain certain parts of it, like a PDF report from a certain source, and then combine that with some image data from somewhere else and bring all of that together into one particular graph with a particular domain information baked in. But in the future, let's say you had new information available, you build another graph, not necessarily in the same system, but essentially a different graph with a different domain sort of expertise in there. But thanks to the power of the agent above this, now you can build like MCP servers or other things that allow you to interface with these different systems. So you don't necessarily need to build one large graph and derail the entire project by having too much complexity baked in at a very early stage in the pipeline. And I think a lot of organizations are slowly realizing that with these modern tools and the ecosystem that is available now, it's a lot more feasible to build these graphs on the fly using these traditional, like different non-traditional techniques of bringing data from different systems. Totally.
And I think that's a fascinating concept that we've been also iterating with is the idea of small graphs or combining two graphs together. Because one thing that we have at Hedgineer is like, we'll work with a hedge fund that has their own bespoke understanding of the world. They have their own graphs that, whether they know them or not, are very conducive of turning into a knowledge graph and using something like Kuzu for. But we also come to the table with a lot of knowledge about what are the best systems, what are the best tools, how does Bloomberg integrate with CapIQ? How do these different data vendors actually play nice together? What is the best practices for doing a shadow nav or constructing an IBOR or constructing an ABOR? And I want to be able to take my knowledge graph that we're constantly curating and refining and making better and be able to have that be essentially like a CP of the .kuzu file into a file system, construct another knowledge graph within their file system, and then be able to blend the two together. So like you had knowledge about your world, but we're bringing knowledge about this entire ecosystem. And the second that you plug that in, your knowledge as an organization gets exploded, and you don't even have to hire a single full-time person for that. Like a lot of times you have to hire for expertise, and you have to bring that in as an expensive FTE hire that honestly, if they could just tell you what they know and then have agents go and run with that, you don't need to have them as a full-time person on your payroll. And so the concept of being able to bridge two knowledge graphs together, and you have an entity or an organization, and that's how we think ourselves, we bring that knowledge graph to the table, And if you just plug that into a system that works efficiently with knowledge graphs and you build up your own knowledge graph around your research process, it becomes pretty powerful. And like this concept of interoperability of the Kuzu protocol, I think is something fascinating. And I'd love to see that if I could put anything kind of on like the roadmap or in the zeitgeist of the Kuzu brain, that would definitely be it.
Makes total sense. Yeah, no, we're keeping all of these developments in mind as we design the system and improve on it.
Yeah, I'm curious now. I'm going to question a presumption that I made earlier, where the graph is not the primary store, and we have had this conversation a couple times internally at Hedgineer, where we're starting to get a lot of value out of the graph. And should we, when we can, start treating the graph itself a primary store of information data that doesn't have another source that it originated from, gets transformed and then stored within the Kuzu graph? And we go back and forth. I'm curious on what you're seeing right now. Are you seeing many Kuzu users or just graph users in general using Kuzu as a primary store of data and information, or as a secondary semantic layer that sits on top of a primary store? And for people that are a little confused about the question, a primary store would be if I have a customers database with a set of products, and those both exist within a SQL table called products and another SQL table called customers, and then maybe I have another table called orders. And so all of the orders and the products and the customers I ever had all exist within those tables. There might be some interesting relationships that exist among them that's hard to disentangle by writing a SQL query. But if I were to take those concepts and create a products, customers, and orders table, or I guess it would probably be products and customers, and orders is an edge between the two, I can then start using Cypher to do more interesting queries. And if you start using that a lot, you might say to yourself, should I actually just be storing the products, the customers, and the orders as a Kuzu database itself and not having that separate SQL store and using it as a primary storage mechanism? Now, in that specific use case, I'm sure there's a lot of reasons why it might not make sense for that, but there are scenarios where it starts being a bit of a gray line. And I'm curious what you're seeing from your vantage point on Kuzu being a source of primary versus secondary storage.
Yep. So yeah, I definitely think the latter is more common, which is the graph is still not the primary store. People tend to bring the data from other systems. And let me explain how I see a lot of use cases these days. The current way of long-term data storage, at least in most large organizations, is what we call data lakes, where you have these cloud storage buckets. All the major cloud providers provide a version of it. S3 is the one on AWS. So if you think about the cost implications of long-term storage, S3 and all these other cloud storage systems, they are extremely cheap. You have all these tiers. You have cold, hot storage, where you can actually really long-term store things for almost for free. And these can store terabytes of data pretty much at very, very little cost. So what I've seen people, large organizations or even mid-sized organizations do is they tend to persist their data in formats like Parquet or any of the other data lake formats that have become popular, such as Iceberg tables, Delta Lake, the Unity catalog. So there's a lot of open source formats now, especially these catalog-based formats that sit on these cloud storage systems. And the benefit of those is those are universally accessible to a lot of other query engines. DuckDB can seamlessly scan and query those. LaunchDB can do that from the vector side. So there's just so many different systems now that can plug into these data lake storage layers, do the specific kinds of operations they need on them in a general purpose way so that you don't get locked into one particular paradigm of query operations. So Kuzu actually is designed to seamlessly fit in with that sort of model as well, where we don't assume that people want to store their data in, you could say, the Kuzu native format long-term, because let's say tomorrow you had another use case for that very same data that benefited, let's say, from a SQL query. Let's say all you needed was an aggregation query that wanted to calculate the average price of all the products purchased in the last month. Now, that is just a very simple aggregation that you could have written in like 3 lines of SQL. You didn't need a graph for that, right? So the way we see it is that the different the databases, embedded databases out there, and these query engines now like Polars and DuckDB and all these other systems, like there's so many different ones out there. They're all unique in the way they optimize for very specific kinds of query workloads. And in any scenario, you can always imagine a different kind of workload that came about for some different use case, some business use case. So you would want your data to be more or less universally accessible in these kinds of formats. And Postgres actually is still a very universal format, even though it's in its own database layer. Postgres is very well connected with the rest of the ecosystem as well. So it generally does make sense to store things in a relational system that already has a structure associated with it and is easily pluggable to these other different ecosystems out there, while Kuzu seamlessly fits in. And when you need a graph, when you actually need to scale the graph workloads, Kuzu can just step in as necessary.
Mm-hmm. But one of the, and I guess I totally agree with, I mean, I generally totally agree with that. But the challenge that you then have when you're working with a graph, not a priori, but after the fact, is that those relationships that you have to extract out from the data within the data lake may not be as obvious after the fact, and they might be a priori. And so if you actually write the inserts or create a table or something that captures that relationship or like the edge of the graph, it makes that creation of the graph hopefully a little bit easier on the back end.
So just to add to that, you're totally right. You can basically just, in that scenario, what you're saying, to keep a log of what data models were used and potentially version this over time and potentially have backups of your data. It's totally possible to do that in Kuzu, right? You just define your code and your schema, just like you would in a relational system, and you commit that to a repository. So you have like a commit history, and you know how the data model has evolved. But now you also have a database on disk, right? Essentially, a Kuzu database is just a file on disk. Mm-hmm. So it's very trivial to just back up these files, which represent a snapshot of that database at any timestamp. And you can pretty much have like an arbitrary collection of these snapshots, because storage on S3 and these other cloud storage systems is basically free. Mm-hmm, mm-hmm. So we've seen a lot of users actually go down that road where they actually archive their data as just files on disk, retrieve the state of the graph at that certain point. And then if the data model evolves in the future, let's say they have some new use case where you have new nodes and new edges that came into this graph. Obviously, the data model has diverged from what existed before, but you have the entire history of how the data model has evolved. You have all the code to reproduce the creation of that graph from the source data. So it's actually really trivial to point your code base to whatever source of data you have and re-ingest a very large data set on demand in the future, because that's the other benefit of Kuzu, which is it's extremely rapid at data ingestion. You can ingest millions of records in the order of seconds. So it's a very cheap operation to store this data in something like a data lake, archive all the code, have the data models versioned, and you have all the evolution history in your repo. And now you also have the ability to reproduce these on demand and snapshot the databases. There's so many different ways to actually access the state of that data model at any point in time, depending on the needs of the application.
Yeah, and being able to tear down and rebuild the graph as we get new knowledge or feedback for a specific use case has been very powerful. And being able to snapshot, I mean, we've just been storing a lot of times the graph in Git, and we could go back to the graph at a certain point in time and see what its state was relative to the code. If it's not overly large, or you can see like the location that it might be at in S3, and it's always just like opposed to an append model on the graph, you just recreate the graph, put a semantic tag on it, and then that is the state of the graph at a given point in time. Do people use Alembic with the graph creation at all? You were just saying that. I'm curious if you see that.
No. So again, Alembic. Okay, let me take one step higher than this. So for folks who are familiar with the ORMs, object relational mappers, and essentially what Alembic does, you can version your SQL data data models. Right. So the way I see it is that the way people use Alembic and SQL Alchemy, for example, that's the most popular client they have. They are very optimized or tuned for these record-based operations. These come from an era before columnar systems were the norm, right? They predate DuckDB and ClickHouse and all these modern columnar stores. So the use case for those is very transactional. When you actually have data that is write heavy and you want to do a lot of individual writes, like things like going to Postgres and other systems like that, it's great. But the moment you step into this analytical world, like if folks who've used DuckDB would know this, you want to process data in bulk. You want to be able to bulk load the data from whatever tables you have, not go record by record. So even though DuckDB does have some connectors to these systems and these sort of ORMs, I'm not sure how Alembic integrates with these SQL systems. I don't think they fit very well, is the point. So Kuzu is very much in the same vein as that, as how I would say. We don't have an equivalent for that.
I guess I was thinking of Alembic more for migrations in DDL schema, whereas because Kuzu itself is inherently strictly typed, that the DDL is inherently tied to the state of the DDL for Kuzu at a point in time. But I guess in the scenario where you're not really doing inserts over time, you're a lot of times just recreating the graph from scratch. The DDL doesn't really have any sort of evolution. It's torn down, recreated almost at every new instantiation. It's not something that's incrementally getting inserted to, because it's not a primary store, right? Like the incremental inserts are happening within the primary store, whether that's in whatever the data lake is, and then at any time you can recreate the Kuzu graph on top of it, but you're not necessarily doing those inserts at the same time, although you could when it's being written to the data lake.
But to close that point, actually, I think there could be a version or like a concept of Alembic in the structured graph world. It's just that I think Kuzu is the only one out there right now that does this. There's not that big of an ecosystem around this kind of structured approach to graphs. So who knows, in the future somebody might actually write something like that.
Yeah, because really all Alembic is there's like the Alembic tables that get auto-created within the relational model that has the Alembic version, and you can know what version you're on, and then you have the apply and the rollback methods in a Python object, and all those are eventually compiled to SQL DDL commands, and then the rollback is no one actually ever uses rollback in Alembic, by the way. That's just I don't know anyone that's had the hygiene of keeping a long migrate or evolution plan in Alembic and keep all the rollbacks up to date. If anybody has, I'd love to hear about it. But anyways, totally. There's another question that I've been having internally around ontologies that get constructed within knowledge graphs, and that is, how much do you lean on AI to determine new values in a given node's attribute? So, for example, like let's say you have an investment idea, and one of the nodes can have theme. And theme can be a user defining that theme, or it can be AI trying to find some common value in a cluster analysis, but it's not actually human curated. And that same argument can be made for all of the different attributes on both nodes and edges within a graph. And it's very easy to let AI run wild and determine the values. It can't actually create, as long as you don't give it access to DDL changes within Kuzu, that's not a problem. But the actual values that get instantiated within the Kuzu graph is a question that we ask ourselves internally a lot at Hedgineer on how much do we allow the AI to determine those values, or do we put them in an explicit set and the AI has to choose? And the former, you might get some insight that you maybe didn't have already, that the AI captured something you didn't, but you lose a little bit of that strict control, whereas the latter, you have explicit determined options that you can choose from. Those inherently work within your workflows or organization, but you're kind of afraid you might be missing something. Are you leaving something on the table? And I would love to get your thoughts on that. We think about that all the time. I don't think there's a silver bullet, necessarily a right or wrong there, but I'd love to hear from you on where you land within how loose you allow AI or humans to be when determining values within node and edge attributes.
Yeah, so I think there's two parts to this. There's the ontology extraction from an LLM to define essentially what nodes and edges you want to capture from your data. And then there's a downstream step of actually using that structure and building the graph out of that. So the part that I think I've seen some users in Kuzu do, our user community do, is they're actually looking into using LLMs for this ontology extraction. Now, every domain has its own specific vocabulary. I'm sure finance and hedge funds have their very specific structures of data that they're trying to extract from these different sources. So I'm a big fan, like just like you mentioned, of a constrained approach. Like, don't allow the LLM to go fully free form and produce any kind of output based on what it thinks is right. I would say like provide some kind of constraint on these are the bounds or the categories of things that we would expect. Classify these accordingly. Again, it becomes a structured output problem, right? You look at the data, you allow the LLM to understand what is in there, and then you allow it to actually constrain itself to a certain set of range of outputs that it could produce, rather than just saying, do extract an ontology and give me something that fits this domain. Completely loose sort of extraction processes that way tend to not be very useful because you lose the benefits of what a graph provides. Inherently, a graph is a way to impose structure on data that was otherwise unstructured. So if your LLM is allowed to just extract any edge representation with any sort of edge label, that kind of defeats the purpose of having a graph. You might as well have just gone down the vector road and just had like a fuzzy blob of unstructured text to begin with. So I definitely lean on the side of more structure is better than less, and some level of constraining the LLM's output is better than none. And yes, there is a bit of a balancing act to do in terms of how constrained you do it, right? Like you don't want to have a very rigid sort of schema where only these things work, but then a couple of months down the line, you have new data that came in that does not align with that schema. So I think where people need to really think about this is the power of a graph is the flexibility of data modeling. Now, what do you mean by flexibility here? Essentially, it means when you have a current data model, that does not mean that it is set in stone. Let's say you have, I don't know, three node tables and 3 relationship tables. You have the edges between them accordingly. Now, let's say a new form of data comes in where you had a 4th node table and a new edge. So an additional node and edge type that went into your data. Let's say you had a graph update that essentially updated all this information. Now your new data adheres to that new structure with 4 nodes and 4 edges. So the beauty of this is as you go through this evolution and the data evolves, the ability for the user to go in, understand the data model, tell the LLM, these are the things I need, re-ingest the data into a graph that adheres to that model, and potentially understand the limitations of that model, migrate to a new model. All of this is very, very trivial because it's just a few lines of DDL that change and you re-ingest the data, right? So this goes back to my previous point about having the graph as like a secondary data store and operating really well with the existing data that you already had, whatever form it was, JSON or relational tables and whatnot. And this makes it very, very fluid in terms of how you go about it. You can actually apply LLMs in a very, very flexible manner, understand what data models suit the current state of the application, extract your ontologies, define the data model explicitly, write the DDL, and then allow yourself to evolve that data model over time as the use cases evolve as well.
Yeah. I in this role of the primary and secondary relationship that Kuzu has with the actual primary storage for us has been so powerful. I'm pretty convinced at this point that you can do any type of analytical workload with 2 MCP servers. One can write SQL, the other one can write Cypher. And then there is context and knowledge around the two. And giving that to anything like a Claude Code or Anthropic Desktop that can iteratively allow the relationships between the two to be navigated and traversed to be able to solve any problem from like any enterprise problem. Like that's essentially what we're starting to stumble on, is that by interacting with these two systems where you have one data lake, it can be queryable in a lot of different ways, whether you use Databricks or you're in a Snowflake environment or you're using DuckDB. Honestly, like DuckDB is very powerful. It can be very heterogeneous in terms of how you want to access it. And then just make sure that the semantic layer of how those systems, workflows, people, processes, reports, upstream systems, all are defined within the semantic layer of the graph that has explicit relationships to the primary stores. So like you have definitions of like your gold tables within the graph, the concepts around the business of those gold tables, the reports that are generated from those. As long as those exist in the semantic layer of the graph and the primary source is available within wherever you're going to access it, but maybe it's accessible to DuckDB, you could pretty much have AI do anything you want at the enterprise with DuckDB, Kuzu, and an MCP server that can write SQL and Cypher, and the right context around that. All of the other things that we're building in the AI space, I think they're honestly like, they don't matter as much. If you can just do those couple things right, you can go incredibly far.
That's a very good point. And Kuzu, actually, I'm not sure if you've read this and should point this out. We have a blog post on blog.kuzudb.com that talks about how to use the Kuzu MCP server to do some interesting stuff regarding querying the data via Cypher. And one very interesting thing that we floated an idea internally on is, let's say you have your data in a relational system like DuckDB or Postgres. They already have their own MCP servers. But let's say you did not yet have the Kuzu graph. Potentially, you could use some sort of bridge, a connector from the MCP servers of those relational systems to bring the data into Kuzu. And now you have a database in Kuzu that kind of leverages the DDL for that is based on the foreign key relationships in the primary store, in this case, relational systems. So imagine that stage one where you bring that data from those systems into Kuzu, and then stage two where you use the Kuzu MCP server to expose this functionality to some sort of agent above it. And now you can basically interplay very smoothly, as you said, between these, where the agent chooses whether the SQL query is more suitable or the Cypher query is more suitable, depending on the kinds of questions being asked.
Totally. I mean, we do the same thing. Like you put a CLI around write SQL or a CLI around write Kuzu. Underneath it, it just connects to the kuzu.db file and it converts the Cypher the question to Cypher, and then the same thing with the question to SQL. And then you allow Claude to construct the actual underlying query. You don't even need MCP in order to do that. Anybody that's familiar with Claude Code or with Codex could open up a Claude Code terminal right now, say, all right, I want you to write me a CLI using UV and PEP 723 to define the dependencies for a SQL query tool that accepts SQL and then executes the SQL with pollers and returns back the values in a pipe delimited result to standard out. And then also do the same thing, but for Cypher, a CLI tool that imports Kuzu using PEP 723 and writes Cypher query and then returns back the results in a tabular format. Make sure the pipe delimits are the same between the two. And for the SQL connection, and then whatever you want to use for the SQL connection, add that in there. And let me know when you're done. Store both of those in a tools directory and have the first one called dbquery.py. The second one is kuzuquery.py. Done. Right? Like that's it. That's literally all you have to do. Forget MCP servers. Like, yeah, they sound really cool. Then go into that Claude Code session again. All you have to do is write any damn question that you want. And Claude Code already has the context of like, okay, well, let me go and try to query the database. Yes, it has to have some semantic understanding of what's in the data. Throw that in a damn claude.md file. What are like the high level tables, the use cases, and what's in the semantic graph? Put that in another claude.md file talking about Kuzu. And what's actually in the semantic layer, and it's done. All of these like other vaporware tools that exist out there, like you literally could do a $500 million company with that prompt. And it's so simple. I was also touching on one thing there that I'm in love with, and that's PEP 723, which it allows you to define what the dependencies are for a Python script without having to have a requirements.txt or project.toml. Yep. And what's really cool on that is that UV is so damn fast. It's installing Kuzu or installing pollers that it's the same amount of time that Python almost takes to be able to precompile the actual script.
It's amazing. I'm a big fan of CLI tools exposed to these agents. It's just such a powerful concept. And as you say, UV makes it just running these so simple. I mean, dependencies are just lightning fast when you want to install them.
Totally. And then like you want to have a new, so that's like the bottom layer, right? That's the bottom layer semantics, Cypher and SQL. Like there has to be some additional logic or transactions or interaction that can sit on top of that. And so you slowly build these abstractions that can sit on top of it, but put those in a CLI opposed to a prompt, although that's something that we go back and forth on all the time. Like at what point do we put that into a prompt? And then we can touch a little bit on DSPy in your work there. Or do you want to have this be a deterministic workflow and just put that into another tool that's one layer above the underlying SQL and Cypher? And then how do you start evaluating which of those two options are better, whether tool or prompt, deterministic or non-deterministic is the best approach for a given workflow? And that is what we crunch on every day. And DSPy is actually like a kind of a great in between the two, where it is relying on the non-determinism and intelligence of a language model to do things that are a little bit hard sometimes to codify, but it does have almost the IAC like framework for code of prompts. And I've seen you be writing a ton about DSPy, and I'm curious on, one, what has your experience been with DSPy and what are some things you've learned about it? But also, how does it start from your perspective? Is this like a good analogy of actually bringing some more deterministic structure and framework around prompts that kind of looks like code, but not actually going all the way of having the predeterminism of having like an explicit module and function that doesn't have the flexibility of a language model?
Totally. Yeah. I can start by explaining why I'm interested in DSPy and why I think it's a great complementary tool for people working with Kuzu and graphs. So my main interests came about because as I was doing prompt engineering in other frameworks, I realized that these loose text-based definitions of instructions on how to translate the graph schema into a valid query or turn the retrieval into a useful answer, all of those had very finicky, you could say, fluctuations when I change a minor symbol here or there, or when I move a sentence up or down. There were significant differences in the outputs in terms of whether the query was right or whether I even obtained an answer from the graph database. So that's when I began really questioning, how do I go about this prompt engineering task in terms of more reliability, more structure? So when I began seeing what DSPy was all about, I was initially very confused, because everyone talks about it as this prompt optimization tool. At that point of time, I was like, I'm not sure if I even need optimization. All I need is a prompt, right? Mm-hmm. So as I began using it, though, I began realizing it's not necessarily about optimization. Yes, optimization is available, but that comes at a later point. The initial benefit of DSPy is the programming model that it provides. The programming model is essentially, as you mentioned, providing structure alongside the prompt. The prompt is not just a blob of text that the user puts in. You do add some amount of user instructions in natural language, but there is a very concrete definition of input fields and output fields in pydantic models, where you can actually define concrete structure as to what goes into the LLM and what comes out of the LLM. And this is very powerful because now when I'm doing things like text to Cypher or just generating queries in a way that I can retrieve data from my graph, I can very clearly specify this is the structure of the schema that I'm putting in. I obtain the schema from Kuzu in a certain format. Now I validate that as a pydantic model. I send that as a structured information into the prompt. And in the prompt, I add domain-specific things like, for certain relationships, don't do this, or don't give me Neo4j syntax, whatever. I can specify a bunch of different custom instructions in there. Mm-hmm. But the combination of this instruction with the structured inputs and outputs is what actually makes really a big difference to the quality of the outputs. So through this approach, I've been finding that I can build composable pipelines really easily. And the reason I've been writing so much about it is I think people gloss over the fact that this composability and writing clear, concise, modular code in a way that you're actually just interweaving these LLM-based steps with deterministic steps. That's exactly the benefit of DSPy, right? It's meant to help you program with LLMs in a way that you can actually bridge that gap between full automation, fully agentic loops versus some level of predefined workflows. So that's kind of where I've been finding a lot of productivity. The code is very readable. I've been getting really good results, actually, even without any optimization. So the next step is basically, can we run prompt optimization to further improve the quality of the queries that these models write? Like right now, I can get very good Cypher query outputs from these state-of-the-art models of today, like GPT-5s and GPT-4.1s and so on. I'm trying to see if we can potentially run a smaller model, like an open source or like a very cheap model, but trained or optimized on the data queries that were written by a more expensive model, kind of like a teacher-student approach. But unlike traditional fine-tuning where you optimize the weights of or rather tune the weights of the LLM, in this case, we are not touching the weights. All we are doing is operating in prompt space. We can achieve so much more by just getting more out of the prompt. A few words change here and there. A human cannot really know whether this word change can impact things in a different way downstream. So the optimizer's job in DSPy is basically provide that evaluation as well as the examples in a way that now the human is not the one tweaking prompts. DSPy is the one tweaking the prompt for you. So that's a very, very powerful way of thinking about it. Without any real formal background in whatever these optimizers do, you're able to write your code in a modular fashion, provide the examples that it needs, and just get a better prompt. And from that better prompt, there's a whole ocean open out there, because now you don't know really what benefits you get. There's so many new models coming out. You could try this on smaller models, open source models, self-hosted models. There's a really, I think, exciting landscape out there in terms of what people can do with this.
Yeah, I'm curious to know your thoughts on how DSPy gets materialized, or at least the outputs of those prompts. Because one thing that we use a lot is the Claude Code SDK running as a process or a daemon in parallel. And when that's the case, a lot of times the claude.md files or the knowledge in the form of readmes is actually structured prompts many times, but they've been kind of predefined. Whereas with DSPy, it's, at least my impression is, a lot of times it's produced on the fly or at query time and not necessarily persisted. Do you see, if we wanted to use that type of model where we're relying on like Claude Code running in a server like REPL environment, that we just allow it to loop, to leverage DSPy through like a CLI, that we would say, opposed to like getting knowledge from reading files, get knowledge from reading these prompts to help construct the context? Or do you see using DSPy in almost a pre-compile time where you run through all of these prompts and serialize them down to disk in the form of files as being like the one of the two options of how DSPy could work in a workflow like that?
Yeah, so I think there's a bit of a, like, I would say, clarification about how DSPy generates the prompt, right? So let's start with that. Your idea is spot on. You could very much use an agentic framework like Claude Code or anything else on top of a CLI tool that DSPy exposes, which is basically a text to Cypher function or any Python function. And that function could call LLMs and do a bunch of other things under the hood. But now how the prompt itself is generated and how it's persisted, right? That's a part we need to clarify a bit. So DSPy is essentially, the prompt generation process is deterministic. The way it does this is you have a concept of a signature. A signature is essentially like an abstraction above the prompt. And the purpose of the signature is to combine the structured representation in code with the user instructions in natural language. So you could think of it as like a wrapper on top of a prompt below it, which the human does not interface with directly, but the user only interfaces with the signature, which is in code. Now, the signature uses something called an adapter under the hood to translate all of these instructions that the user gave and the type system and all the other things in the signature into a prompt. And that is a deterministic process. So it's not, even though it generates the prompt on the fly at runtime, it's not generating an arbitrary prompt at runtime. It is generating a deterministically reproducible prompt at runtime. So when you persist a DSPy program to disk, when you do a module.save, like there's a .save method, you essentially dump out a JSON blob. That JSON blob persists all this information that's necessary. It has the signature instructions, it has the types, it has all the variable names, all the stuff persisted in disk, right? And that's basically what a DSPy program is. Now, in the future, let's say you want to improve or optimize the prompt. You provided the examples, you run an optimizer on it, persist that new program to disk. Now all your signature instructions and all that stuff has been updated. But the next time you run this module, it's going to retrieve those instructions instead, the so-called optimized instructions. And now the new prompt that's generated is basically on a better version of those instructions that the optimizer generated, not that the human generated. So if you think about how this would be used in your scenario, it would basically be that you would write a DSPy program, you would write your signatures and the underlying modules, and essentially persist the module to disk. Now, when you have the module and the functions and all that stuff in your program, you have like a CLI tool that you expose, point it to the function that you want to call. It could be any DSPy function. You could have a combination of modules exposed as a function, or just a single module, or have multiple modules. There's different ways you could architect each of those stages of your workflow, but all of those would be available as tool calls in your agent above it. So yeah, it's a totally valid way to go about using it. And I think, yeah, that's where the power of DSPy is. You don't necessarily trust the fact that you are capable of writing a very good prompt. You want to use real world examples and lessons that you have obtained from production systems and production data and send that back to an LLM to help optimize the prompts for you.
Got it. Yeah, really cool. Actually, another question. So on that, the DSPy module, when you say that, is the DSPy module the same as a Python module, or is it a separate concept?
It's a separate concept. Yeah. So let's clarify that as well. So DSPy essentially has 3 core abstractions: signatures, modules, and optimizers. So signatures, as I mentioned, is kind of like a replacement to prompts, like text-based prompts that you will have in other systems. The module is essentially the core logic of your program. The module is responsible. In DSPy, a module is basically just a class, and the class has a special method called forward. Now, the purpose of this is basically you write it in that syntax so that in that forward method of your module, you can compose together arbitrary logic that could be LLM-based or deterministic programs or deterministic functions. So depending on what you're doing, let's say you're doing something like RAG, you want to do a database call, that's a deterministic thing, whereas you have a answer generation system downstream, which is depending on an LLM. So all of that could be implemented using for loops and traditional Python code, right? So a module is just a special way of expressing your logic in Python code. But now the module is essentially the core unit of your DSPy program. It relies on a signature to generate the prompt for it, but it is what executes the program and runs the LLM calls and all the other stuff that requires the combination of LLM and deterministic logic. And then downstream of modules is optimizers. Optimizers operate on the module. So the relationship between the signatures, the modules, and the optimizers is very, very, you could say, holistic, where they all operate together and they understand each other really well. But all of this is basically Python programs, right? You persist the code as Python files. It reads like Python code. It's essentially Python code that you would write by hand, except you use these fundamental building blocks, which is signatures, modules, and optimizers. And all a DSPy program is basically a collection of these different modules that execute the final task that you're trying to do.
Got it. Does the module have non-deterministic DAG workflows?
Yep. So you could build an arbitrarily complex non-deterministic workflow, but inject LLM-based workflows as part of that anywhere you need. It's just basically like any Python logic, right? Like any sort of the AST tree in Python, you could just have like any sort of combination of deterministic or LLM-based logic baked in.
So yeah, with that, what's coming up next with Kuzu? I'm curious on the project as a whole. Like, what are the power users that are using it expecting out of the next couple of releases?
Yeah, absolutely. So we have another release coming up soon. But in general, I think, as you know, Kuzu is open source. But we have an enterprise version. We have like the idea of making graphs accessible and available to anyone with a very, very low barrier to entry. So the power users of Kuzu are thinking about it in different ways. They are either using it in memory or on disk. Some of them are using it in LLM-based applications like agentic applications. Some of them are not even using LLMs. They're just using traditional graph-based workflows. But that's again, the power of Kuzu is it's designed to be easily available to people who need graphs. And when you know you need a graph for your workload, Kuzu is that system you could go to for these different kinds of operations that you're trying to do. It's interoperable. It uses Cypher. And yeah, I think the idea is that Kuzu is available. It runs on any system. Because it's embedded, it's compiled independently for every operating system and every platform that we release on. So you could pretty much run Kuzu on the cloud, in a mobile device, in your laptop, pretty much any operating system or any system that you can think about. And the way we see this going is because of the wide range of applications and scenarios in which Kuzu is used, we're going to see graphs reach places where graphs were not there before, right? Like edge devices. Just like SQLite is pretty much deployed on pretty much any device you can imagine, we imagine that people are going to use graphs in these so-called non-standard environments. And I think that's where we're really excited to see where the next stage goes to. Each release, I think, of Kuzu builds upon the previous one. We're adding a lot of graph algorithm capabilities in our upcoming release. We already have graph algorithms like natively running in Kuzu, things like PageRank and other algorithms, but we're adding more to those. The concurrency is another big aspect we focus on. Reads and writes, how do you make those concurrent using MVCC? So there's a lot of, you could say, cutting edge database research as well as techniques from these modern OLAP systems coming into Kuzu based on most recent research in the last couple of years. And yeah, we'd love to see how people are using Kuzu in a variety of use cases. Check us out, kuzudb.com. We're open source. Check us out on GitHub as well.
Yeah. And with that, Prashanth, thanks so much for coming on. And for everyone for listening in, thanks for tuning in to another episode of the Hedgineer Podcast. I am your host, Michael Watson. We try to produce these every 2 weeks, usually releasing on Tuesdays, but don't always hold me to that because the weeks get pretty crazy. And you can follow us on TikTok, Instagram, Twitter. We do a lot of stuff on LinkedIn. Also subscribe on Spotify and Apple Podcast. And until the next episode, we will see you later.